Hello everyone. We're going to be talking about energy and collisions. In an isolated system, momentum is always conserved. Energy is also always conserved. However, a kind of energy called kinetic energy, which is associated with the mass and the speed of an object, is not always conserved. So we're going to consider a couple examples of how these principles, momentum and energy conservation, are applied. Here we have a simple elastic collision like we considered in the last chapter. We have car A moving to the right, and it collides with a stationary car B. After the collision, the two cars end up with two different velocities here. One thing that you'll note is that the relative velocity between the two, here we have A is moving 0.6 meters per second towards B, and here we have B is moving away from A at still 0.6 meters per second. This is given by this formula here, talking about the relative speeds, and it says that the relative speed between the two cars in an elastic collision is fixed. This comes from the fact that the momentum is conserved and the kinetic energy is conserved in a collision. So in an elastic collision, we have both momentum and kinetic energy conservation. Here we have an inelastic collision between car A and car B. Car A is moving at 2 meters per second. Car B is moving at 1 meter per second. Eventually, car A is going to crash into the back of car B, and in this crash, they get stuck together and they move as one. So how fast are the two cars moving after this collision? So in order to solve this, we need to know the masses of the two cars, and I've given that here. So B is going to weigh twice as much as A. So A only weighs 1 kilogram, B weighs 2 kilograms. And what we're going to do is we're going to check on whether kinetic energy is conserved or not. Momentum is always conserved. So we're going to use that to be able to find out what the final velocities are. So our initial momentum is going to be equal to mass of car A times VA plus mass of car B, VB initial. So we can use what we know. We know car A is 1 kilogram and it's moving at 2 meters per second. And B is 2 kilograms, but it's moving at 1 meter per second. So we can see here we got 2 plus 2, so we're going to end up with 4 kilogram meter per second. Let's now look at our final momentum, and so we're going to end up with MA plus MB. And in this case, they both move as one, so let's just call that V final, and that's what we want to find out. So MA plus MB is just going to be 3 kilograms V final. Because momentum is conserved, we have PI equals P final. So we're just going to set these two equal to each other. And so this is going to give us that V final has to be equal to 4/3 meter per second. All right, so now let's check how much energy we have initially. So initial energy is going to be the sum of the two kinetic energies for A and B. So we're going to have 1/2 MA VA initial squared plus 1/2 MB VB initial squared. And we can plug in what we know. Here we have 1/2 MA is just 1, and it's moving at 2 squared plus 1/2, 2, 1 squared. So this is going to be 4 over 2, so that's 2, and then this is going to be 1, so we just end up with 3 joules. So now let's look at our final kinetic energy. That's going to be 1/2. Since they both move together, I can combine these two terms and get MA plus MB V final squared. So here I get 1/2, 1 plus 2, that's 3, and then V final, which is this 4/3. So I'm going to end up with about 2.7 joules. So initially we had 3 joules of energy. After this collision we had 2.7. So you could go, well, delta K is final minus initial, 0.3 joules. That's not such a big deal. But to a physicist it is. We have pretty much the same setup. We have A moving to the right at 2 meters per second. We have B's moving at 1 meter per second for its speed, except now its direction is the other way. We're going to use the same masses that we had before. And now we're going to ask, what is the final speed of these two objects? So our initial momentum is going to be MA VA initial plus MB VB initial. So A is moving to the right, so that's 1 times 2. B, however, is moving to the left. So his mass is 2 kilograms, sorry. But he's moving to the left, so we have to remember to put a minus 1 here. So we're going to end up with 0 is our initial momentum. So now we can look at our final momentum, and we're going to have A plus B, since they move together, times this V final. And so it's pretty easy to see here that V final is going to be 0 meters per second. So after they collide together, they just stay stationary. So our initial kinetic energy is this 1/2 MA VA initial squared plus 1/2 MB VB initial squared. And this is still our 3 joules. The kinetic energy didn't change just because B is moving to the left instead of the right. Kinetic energy only cares about the speed of the objects, not the direction. Our final kinetic energy is 1/2 MA plus MB V final squared. And since the speed of this wreck is 0, we have no kinetic energy. So here all of our kinetic energy was lost. Momentum always conserved, energy always conserved, but kinetic energy is not always conserved. It is only conserved in these very special kind of collisions called elastic collisions. All other kinds of collisions, some amount or even all of the kinetic energy is lost. Let's consider a case where not all of our kinetic energy was lost and work out how much energy is lost in this basketball that's bouncing across the floor. So here we're going to drop it from some height. So here we're going to drop our basketball from some height, let's call it about 1 meter. We know the mass of a basketball is 0.6 kilograms. And so let's just work out real quick what's happening at this collision. Because we do have a basketball falling down, colliding with the floor, and now something is happening. It's changing its momentum. So before its momentum was pointing down, and now its momentum is pointing up. If you change your momentum, some kind of collision had to happen. So how fast, in order to find this momentum, we need to know how fast the basketball was moving. So we can work that out. In this case, we don't care about the time that it takes, so we're going to go to those 4 kinematic equations, and we're going to dig up this one. V final squared equals V initial squared plus 2A delta x. So here we want to find V final squared, so we just take the square root of this. Since we're dropping it, V initial is 0, so we just are going to end up with the square root of 2gh. So here our V final is going to be the square root of 2 times 9.8 times 1 meter, and this is going to give us 4.4 meters per second. So the basketball is moving down at 4.4 meters per second, and now in order to find out what happens after this collision, we don't know how massive the floor is. We assume very, very massive, but we don't know what kind of collision this is. Basically, how much of that kinetic energy is lost. That's what we're going to try to find out. So comparing these two heights, this one is half as tall as this, so this is going to be our 0.5 meter. So we can find out this velocity, that it takes the basketball to move upward. So here we're going to have some initial velocity, and through this trajectory that the ball is moving up, it is getting slower and slower and slower. You can see that the ball is getting, these two dots are getting closer and closer together until right here at this point, at the very top of the trajectory. Here V is positive, here V is negative. It's starting to move down again. So that means at the very top, V is 0. So here we're going to look at V initial starting at the trajectory, going up to this V final going to 0. Again, we don't care about time, so we're going to end up using the same equation. So we're going to end up with 0 is equal to V initial squared plus 2A delta x. And this gives us the same equation. Basically that this V has to be the square root of 2gh. And in this case, the h is 0.5, so we end up with the square root of 9.8. And this is going to be 3.1, yes, meters per second. So how much kinetic energy does the basketball have just before it strikes the ground? Well, that's going to be the 1/2 0.6, that's its mass, times this 4.4. And when we plug that in, we get 5.8 joules. And after it collides with the ground, we have 1/2 0.6, 3.1 squared, and so we're going to end up with 2.9 joules. So since it only goes up half as high, it ends up with half as much energy. And we'll talk a bit more about the relationship between kinetic energy and the height of an object was dropped, or that the object goes to, in the next lecture. But here we have that the basketball loses 2.9 joules of energy in this collision right here. In problem 5.8, we have, we're asked to find an expression for the kinetic energy in terms of momentum and mass. So if we go back to kinetic energy, that's 1/2 mv squared, but now we want k is going to be some function of momentum, p. So we have to go back to our definition of momentum, and we get mv. So we need to rewrite this expression in terms of p, which is going to be mv's, basically. So we have a v squared, so it'd be nice if we could put a p squared into here. So let's try that out. So k is going to be 1/2 And now we want to put a p squared in here. So what we ended up doing is having an mv squared. So I'll just show that over here. We're saying that this is mv squared, so m squared v squared, by putting a p squared up here. But that's not the definition of kinetic energy. It's not just 1/2 p squared. We're going to be off by a factor of m, so we need to divide by an m here. So if you plug in what we have here, these two expressions are the same. Here we just plugged in mv for p. And so you can see here that this m on the bottom cancels out, and so we end up with a 1/2 mv squared. So k, in terms of momentum, is going to be p squared over 2m. Alright, so the next problem is 5.9. We have two objects A and B. They both have the same momentum. So that tells us PA is equal to PB. But A has 4 times the kinetic energy of B. So that means KA is 4 KB. So the problem that we just worked out is really going to help us solve this one. So K is P squared over 2M. So let's rewrite this in terms of momentum, the kinetic energy, how they're related, A and B. So we have PA squared over 2MA is equal to 4 times the kinetic energy of B, which is PB squared over 2MB. Now, the other piece of information that we know is that their momentums are equal. So instead of saying PA equals PB, we could just have one number for PA and PB. So we could plug in P squared 2MA is 4 P squared over 2MB. And we can simplify this a bit more because both sides have a P squared, so we could get rid of that. Both sides have a divide by 2. We can get rid of that. So what we have is a 1 over MA equals 4 times a 1 over MB. So what we want is the ratio of MB to MA. So let's just multiply by MB. So MB over MA is going to be 4. So the ratio of their masses is 4. Alright, so in this final problem, we're looking at a physics student driving their car, has an accident with a bigger car, which is stopped at a red light. After the wreck, the wreck moved 4 meters. Police officer calculated the speed to be moving 7 meters per second. So what is the initial speed of the student? Is what we want to find out. So here we're given V final, and we want to know how fast was the student going initially. So our initial momentum is going to be equal to our final momentum. That we know, momentum is always conserved. But we could not say that our initial kinetic energy is equal to our final kinetic energy. This is not true in this case because we have joined vehicles. This tells us that this is an inelastic collision. So we can't use this to solve our problems. So initial momentum is going to be mass of the student's car times V initial of the student's car plus mass of this car that stopped. Let's just call it A, and then VA initial. Well, this car is stopped, so it's just 0. So our initial momentum is just mass of the stopped car, V initial for the student. Our final momentum is given by how fast the the combined rec is moving. So in this case, we're given this V final. So here we have mass of the student. I'm just going to write this again. Plus mass of the stopped car, V final. So I know from momentum conservation that these two are equal to each other. All right, so what I want to solve for is this V initial. So I need to divide this one by mass of the student's car. So here we have mass of the student's car plus mass A divided by mass of the student's car times V final. So here we end up with 1200 plus 2000 all over 1200. And then our final velocity is 7 meters per second. So when we plug this in, we're going to get about 18.7 meters per second.